So first, we're going to derive the v equals v naught plus at squared. And to start, we have acceleration is equal to the derivative of velocity with respect to time. And in this case, for kinematic equations, acceleration is constant. So then we're going to do some separation of variables, put the dt to that side, leave dv over here. We're going to integrate. And for the dt side, we're going to go from 0 to whatever time you want to go to, which is t. And for v, you're going to start with v naught to v, starting velocity to final velocity. Then you integrate, and you get at for this side. You're going to do it with limits, because it's a definite integral, and on this side is v. I'm going to do v and v naught. And then we do at minus a0, that goes away, equals v minus v naught. So then we get v equals v naught plus at, and that's it. For the next equation, we're going to do delta x equals v naught t plus 1/2 at squared. That's number 2. And so to start, we have velocity is the derivative of distance or displacement with respect to time. So we do another separation of variables, and we're going to integrate these as well. The limits of 0 to t and x naught to x. In this case, we're going to replace v with v naught plus at and dt, and leave the rest the same, equals dx x naught to x. We take the derivative again, and so that's v naught t plus 1/2 at squared. And then if you wanted to, then you're also going to take it with limits, and here you also get x with limits. And what we get here is v naught t plus 1/2 at squared minus all that would be 0, so we're just not going to put it for now. And x minus x naught, that also equals delta x. So here is delta x equals v naught t minus 1/2 at squared. And for our third, we're looking for v squared equals v naught squared plus 2a delta x. And in this case, we're looking for velocity with respect to distance. And to find that is this, we're going to take velocity with respect to time and multiply it by the inverse of displacement with respect to time. So flip it over. And that equals acceleration, the derivative of velocity with respect to time is acceleration, multiplied by the inverse of velocity, because velocity is displacement with respect to time. And so that equals delta v delta x. And now we're going to do more separation of variables. In this case, we want v to that side, and we're going to put dx to the side with a. So if we multiply, we get v dv equals a dx. And we're going to integrate again. And this side is from v naught to v, and this side is from x naught to x. And we integrate, which gets us 1/2 v squared with limits equals ax with limits. So do our FTC v squared minus 1/2 v naught squared equals ax minus ax naught. And then we can pull out the a. And we can multiply all by 2, the whole thing. So we get v squared minus v naught squared equals 2a delta x. And to clean it up, to get our what we're looking for, we get v squared equals v naught squared, plus 2a delta x. And that is it.